So as an example of how we can apply the Clausius-Clapeyron equation, I've got a question here, written here, using this equation. This is from the last video. Say we know the normal boiling point of benzene, we can look that up. It's 353.2 Kelvin, and we know the enthalpy of vaporization, the molar enthalpy of vaporization, is 30.8 kilojoules per mole. The question is, what would be the vapor pressure of benzene at 373 Kelvin if we assume the enthalpy of vaporization is constant? All right, and what we need to do here is identify, okay, well, we know P1, the normal boiling point means that the vapor pressure is equal to atmospheric pressure, which is 760 torr. All right, so that's P1. P2 is what we're after. We know T1 is going to be 353.2 because that's the normal boiling point. And T2 we are given in the problem is 373 Kelvin. So now we know all of those, we just need to plug it into the Clausius-Clapeyron equation and solve for P2. Okay, so by the way here, log P2 minus log P1 is the same as log P2 over P1. All right, so we can use that. Okay, so we just need to plug in values at this point. All right, so we'll have log of P2 over 760 torr is equal to, and I'm going to write everything in joules just to make sure that we don't get our units mixed up. So 30,800 joules per mole, that's our enthalpy of vaporization, divided by R, 8.3145 joules per mole Kelvin. All right, so that's to make sure our units cancel here. And then we're going to have 1 over 373 Kelvin minus 1 over, let's move that, 353.2 Kelvin. All right, so we need to solve all that. All right, we'll get P over 760 torr. Now I'm skipping a bunch of work that I've already done in my notes here, but we're going to get E, right? We need to do an exponential of all this stuff here. So all of this, once you work it out, you should get a unitless value. So all your Kelvin and your joules and your moles shall all cancel. And we should get E to the 0.557. So you can double check my work here and make sure I did this correctly. And E to the 0.557 is equal to 1.745. Then we just multiply that by 760 torr, and that gives us 1330 torr. Right, and so that gives us a way to find vapor pressure at a different temperature given a boiling point, right, and the enthalpy of vaporization. That's all we need. Or we could be given a vapor pressure at a specific temperature. It doesn't have to be the boiling point. That's just a convenient value that you can look up. And as long as you're not changing the temperature too drastically, this should work pretty well. As long as delta H is approximately constant over the temperature range that you're considering for delta H vaporization, you should be pretty good on your value here. One final note, aside from this example problem, is that we can do that same integral we have, but do it as an indefinite integral instead of with specific limits. And we can get that we get log of pressure is equal to negative delta H bar of vaporization over RT plus some constant of integration. And this gives us a formula if we can find pressure versus temperature for that coexistence curve. We have a slope here, right? If we plot log P versus 1 over T, right? These are our variables, 1 over T. We can see we should get a line with a slope of negative delta H vaporization over R. And this can be done to find, right, if you measure the vapor pressure as a function of temperature, and you can use this analysis here to get a value for the enthalpy of vaporization. So this is one way of measuring enthalpy of vaporization. And if you do see deviations from linearity here, that would be an indication that your assumption about delta H vaporization being constant is not good. Yeah, so this is actually something we're going to do in a lab experiment. We'll measure vapor pressures as a function of temperature. and we'll basically change. Actually, we're going to change the pressure and measure what the boiling point is. Either way you look at it, we're measuring that coexistence curve, and that'll allow us to determine enthalpies of vaporization of different liquids.